Hello everyone. Sit back and prepare to enjoy this talk from DevFest Montreal.
Inside and under the hood of the different mobile frameworks that are available to us now. I'll start by presenting myself. I'm Mathieu. Been working at WePoint, or previously you might have seen me as Inventive before. We recently changed brand. I've been a mobile developer and in the software development for the past 13 years. Started with Windows Phone, which shows a little bit my age, but I've also worked in mobile, Xamarin, .NET, Flutter, a little bit of Azure and all of that. And I really like to think about the experiences that we bring to the users and how mobile can accelerate those things. So why this topic? It's part of me thinks that we often jump too quickly on just hello world and then we just read the doc and go and try to build an application. But what in the past I've had the chance to work on projects that go a little bit deeper in the mobile space, and it led me to really understand how it works under the hood. And this really enables us to, I realized that understanding the foundation really enables us to not only build something, but innovate on it and bring that innovation to build like greater things on the mobile application. So let's start with like three big categories of mobile frameworks. So on the left, you can see more like the web rendering technologies like Cordova, Ionic. Those use more like a browser type of rendering. They really render like web objects onto the screen. Those were really early in the mobile kind of era of building applications. Then in the middle, we have like Xamarin Classic, Kotlin multi-platform. Those frameworks kind of let you share half of your code, so the business logic, like doing your HTTP calls with your servers and all that is shared, but you're building native views for each. So you're building a view on iOS with iOS code, and you're building the views on Android with Android code. And now in the past like decade, the market is really more towards the latter section with like Flutter, .NET, platform, and React Native, which will do native rendering across the board and share almost all your code that you're reading, you're writing for your application is the same. So the view is shared, the logic is shared, and everything. And that's that section that we'll look into more details today. So if we look at React Native, you're building the, I'll go quickly on overview just to bring everyone up to speed. React Native, you build it on TypeScript. It started in 2015, developed by Meta, and still very, very popular today. .NET had different names, like it started as Xamarin in 2012, then acquired by Microsoft. It was rebranded into .NET MAUI, and now it's built directly into .NET as .NET iOS, .NET Android. Platform is open source and was built right here in Montreal. I've had the opportunity to work on that team in the early days, and yeah, it leverages the .NET iOS, .NET Android method, and also the WebAssembly of .NET to build your application. Flutter was slightly later, 2017, but you can see it's still a long ways ago, and supported by Google, among other players. And it's built in Dart. So before we move on, all those frameworks are really complete and mature solutions nowadays. You'll have success regardless of which one you pick. And so today I want to explain how they work under the hood, but I'll let you like build your own opinion of which framework you think fits the best for your project. So let's start with how they are how apps are drawn on the screen. So there's kind of two categories. You can draw native components, so like React Native, .NET MAUI use that technique. So basically, as you write in your TSX or in your application code, it will take that code and then use the native SDKs to render UIKit views and Android views on the screen. I have a next slide. I have more details on that. And if you look at Flutter, and now platform offers both ways, but trending more towards the Flutter way. Think about it like if you're building a little bit like a game engine. So your Flutter directly draws the pixels on screen, bypassing completely the operating system UI elements. So the difference is illustrated here. So this is React Native code, and you can see what it would render on the right. I'll just do a 3D view so you can see the different layers. So you see the different elements are rendered by the operating system. Those are native views and containers. And then if we do like the transition, so we can see the virtualized list, which is like the list of all the items, is kind of translated into a recycler view, which is the view to render a list on Android. And then the item template, basically the text would become a text view directly on the Android layers. More like with diagrams, try to illustrate all the different categories. Is on the left you'll see your UI code, and then in the React Native world, I'll say is like the purple one. You'll have the layouter that will take your code, do the layout, how to place elements on the screen, and how to kind of build those components, the styling and everything is kind of computed within the React Native system. And then it's sent as native views to UIKit and Android views to render animations and all that. So the blue section and the green sections are handled by the operating system to display that on screen. So if we compare that to Flutter, that's drawing pixels. Flutter is like skipping everything, like get rid of the native views. I only need one, it's like activity, and I'll do the rest myself. So as it's building its own element tree, it's building its own animations, not relying on the animation system from the platform. And as the rendering engine and the embedder, I'll talk more about the embedder later, but that's what kind of allows the communication with the native system under the hood. And then there's a slight layer of native interrupt to transfer user input. So basically the touch inputs and the scrolling from the fingers are passed directly to Flutter to handle those inputs on their own, which is quite different from React Native or other frameworks that will handle the input, but then the input is basically handled by the native view from UIKit. So React Native doesn't really need to interact at that point about the input, like the text box already takes care of that. One key difference you can notice is in a text box, you can like write text, and then if you long press, you see like on iOS a little magnifying glass, and then you can move your cursor around. So in React Native, that would come like free out of the box, but in Flutter, the Flutter team had to like rebuild all of this on their own. There's positive like challenges and benefits to each method. So drawing native components it was more challenging to make platforms look the same, because on each platform you have like some discrepancies on how the operating system renders them. But as I explained with the search box, you get the benefits of accessibility is all built in, like the text selection is all built in, and you get also all the OS updates right away. So now you might have updated your phone recently and saw liquid glass. So like a React Native application, for example, it would be much easier to get liquid glass across the board rather than if you were drawing pixels on canvas, where that it would need to be like re-implemented within that framework. And at the opposite side of drawing pixels, it's easier to be the same across the board if for your brand that's what you're looking for, and keep things in sync is also much easier to do. The animation is also a lot more powerful because you're not relying on the specificities of each animation system on each platform. Since drawing pixels, you kind of control the canvas directly. You can go a little bit deeper. With time and effort, you'll do any animation you're looking for on both sides. So it's not a limitation. It's just as a framework developer, basically, for the Flutter team or the React Native team, it's a different challenge. So we've talked about the view a lot. If we move into more like native APIs, more like things are less UI, I'll share like how it differs from one to the other. So what's a native API? Just to start, native API is part of the iOS SDK or the Android SDK. It lets you access like Bluetooth and location services, biometry, for example, register push notifications. Like there's hundreds of different APIs. They also serve as a way to create views. So leveraging UIKit and Android View would also go by a native API there. Those are exposed in Swift, Objective-C, Kotlin, or Java by Apple and Google. But there's obviously lots of ways to interact with them with other languages. So if we look at one example that's a bit more obvious, like getting your user location. So this is how it would look in Swift. So you're using a location manager, requesting permission, and then listening for updates. But if we compare that to Kotlin code, you'll see the concept is similar, but the classes are completely different. You're using a fuse location service that comes from Google Play services, and yeah, so the concept is the same, but the execution is much different. But as a mobile multi-platform developer, you don't want to deal with, on iOS, let's do this code, on Android, let's do that code. So you kind of abstract that together. The goal would be to use like geolocator, get current position. So that's what you would call within your app. But under the hood, that part is, there's likely a library or someone that already made like an NPM package or a pubdev package that unified those APIs for you and kind of drawn the common denominator between those. And it also creates the interrupt with the native language to access the API, how it works, and we'll see soon how it differs from one framework to the other. And so this would be what it looks like in React Native with the Expo location package. So from NPM, you can install Expo in your app, and you would see basically the same concept again, like location, get the permission, then get the last known position. And this would basically, under the hood, do exactly this on Kotlin and exactly this in Swift. It's just hidden from you as a developer at the application level. You don't see it. But if you look on GitHub and you go in that package code, you'll likely see those classes and all of that. So if we look now on how they would look, how does shared code become two native app, and how it differs from one framework to the other. So high level is you got your code. So in gray, that's what you as an application developer will write. And in the purple, it's like the magic coming from the framework. So if we start with Flutter, you have your Dart code for your application. That's first, and then this sits on top of the Flutter framework. The Flutter framework is written in Dart. It includes your UI toolkit, mostly all the widgets, because in Flutter everything's a widget. So that's part of the framework written in Dart, and it sits on top of the Flutter engine that's built in C++. This is like running Impeller or Skia, depending on the platform, or the mode that you have in your compilation. And it will do like the rendering and layouting on the screen. And this sits on top of the Flutter embedder. Flutter embedder is kind of the last level of glue that mixes C++, Kotlin, and Swift to interrupt with the Android specifics and the iOS specifics of each operating system. And between those 3 layers, or even 4 layers, because your Dart code also existed that, you have platform channels. So platform channels is a way to communicate between those languages. It uses serialization to kind of pass the messages in between. And serialization has some sort of cost because it's not like a direct code access. But it's really optimized in this way, and like it's binary, like it's serialized as binary. It's not passing JSON messages between the layers. So it's as optimized as it can get. And each framework, Flutter included, is still working and innovating on how it can minimize those impacts even further as it keeps evolving. If we compare now with React Native, the concept is similar. You can see you have your application code on top. Then it sits on the JavaScript runtime to kind of execute your code. There's a renderer to do the layout logic and render objects there. And now since the architecture there was a shift like 2 years ago in React Native. Now they have like a JavaScript interface called GSI that's generated. So you have like more of a type-safe communication between this and the underlying operating system with the native renderer and native modules. Native modules is a little bit like the embedder on Flutter. It kind of interrupts with the native APIs, and the renderer fabric is more like on the drawing engine side of things. And it leverages those native APIs a lot because, as we said earlier, React Native really displays true UI kit and Android views on screen. So it's using the native APIs not only to access Bluetooth, but also to create those elements and display them on the screen. I haven't talked much about platform in .NET so far, but it's quite different. So I really wanted to explain it. So in platform or .NET, you have your C# code, again, that's shared across the board. The layout logic is part of .NET MAUI or Xamarin Forms before, or UI if you're using Uno. But really what makes platform in .NET different from the others is the native APIs are directly exposed as C#. They are part of .NET from the get-go. There's a binding layer already baked in from Microsoft. Like as soon as the new APIs are released by iOS, they include them in .NET. So the framework like UI, .NET MAUI, they don't need to interrupt and like serialize messages. They can just straight call in C# an API. This has some benefits that you can call native APIs that are part of Android SDK or iOS SDK directly in C#. The documentation fits more or less, like there's just capital letters that change. So that's quite a significant difference. And now I want to jump into how we package everything. So we've seen how it kind of works with different layers of logic, but now how do we build like an app bundle or an IPA on iOS for each platform? So to get there, I want to first introduce like what is native code. Native code is compiled is code that can be compiled on a specific platform or operating system. So for example, C++ is like the most known native code out there, and then you compile it to either x86 or ARM64, Apple Silicon, whichever you need. If we kind of illustrate it a little better, so basically you have one C++ code, then you compile it and you pick which compilation target or platform target or target architecture sometimes is the word that's used. So then you have the same code, but you'll get like 10 different compilation targets, and only one is good on any machine. So that's kind of native code. And what's the other thing I need to explain is what's a GVM, what's a Dart VM, what's a .NET runtime. So those are virtual machines built specifically for a target platform. For example, the GVM runs Java and transforms it on machine code calls for like to run Java on your machine. And there's a different GVM on every single like OS or platform. Generally, they add stuff that native code does not have, like garbage collections or runtime systems, and more like advanced debugging scenarios with hot reload, for example. There. They also offer, depending on the language, they can offer just-in-time compilation or ahead-of-time compilation to optimize some flows or some architecture levels. I'll get to that into more details soon. So if we look at Java, for example, Java, there's some compilation where it transforms your Java code or Kotlin code into bytecode. Like it's a .class file. And then there's a GVM for each platform that you want to run that code. And it will translate your same bytecode into machine code for that machine. Dart is in just-in-time mode is slightly different. There's absolutely no compilation, and it just runs on a Dart VM, and that outputs machine code there. Dart also has a AOT compilation mode, which will compile your code into like a variation of native code that's specific to each platform. And instead of running on a Dart VM, it will run on a Dart runtime, which is a lot leaner and will like only add what's necessary. So, for example, garbage collection to the execution, and this turns into machine code. The drawback between one and the other is AOT compilation will be like more performant, but you'll have a bigger binary size because the code is like compiled into a bigger binary instead of just being straight up text code, basically. So how do we, now that I shared some basics about like the types of code, now we can look at how we package all of that together. Okay, let's look at native Android app. So basically, APK Android bundle is your application that you would submit to the store. This runs on the Android runtime, which is the GVM for Android, kind of, and this runs on your phone. So Kotlin is compiled into bytecode class because it works like Java, and then you can also add C++ in your native app. So you'd compile C++ to native code, so a .so file, and you put that SO file in your package as well. And then they communicate between each other with the GNI, Java Native Interface. So that's how like native code can talk with Java code. Now, if we compare that to Dart, we can see it. Once we understand everything, it's quite similar. So basically, if you would have Kotlin code, it would be a bytecode class, but in Flutter, you likely don't have too much Kotlin. You have mostly Dart. So Dart is compiled ahead of time, and it outputs, as we saw, a native code. So you'll get your Dart app code as native code in your package, but you also have the Flutter engine that's also native code because we saw it's written in C++ in the package, and the Dart runtime, which is also built-in native code in package. So you have all of that kind of within your application bundle, and it can talk with the native APIs, with GNI, or directly with native code to interact with the system. So that's how it works on Android. If we compare to iOS, principle is quite the same, so I'll go a bit quicker. You have Swift that can be compiled code, C++ into native code, and you get the same principles of Dart going to native code, and you get the same layers basically bundled into your application. And there's like a Swift runtime that's slightly different, but there. Now, changing topics in like differences between how they work on the hood is you have threading, and this is really specific to the languages. It's less so about like the architecture of the operating system, but we saw Flutter and React Native both use Dart and TypeScript, which are languages that can transpile to JavaScript, and they are single-threaded by design. So there's no shared memory or things like that between that language. So you can still do async, you can still do asynchronous code. That's not an issue. But if you want to do pure parallelism or spin out multiple threads to do like heavy processing, you'll face bigger challenges. You won't be blocked, like you can still do it, but you'll face more challenges. For example, if we go specifically for Dart, you can like spin up isolates. Those are ways to kind of parallel or delegate stuff off thread, but they don't have shared memory. So if you want to share like data between different threads, you'll have to serialize those and share them. So they're kind of in between a thread and almost a different process. So if you compare that with C#, which has multi-threading baked in at the language level, if you have multiple threads, they share the same memory. You need to be careful. Like it comes with like responsibility, because you don't want to have like synchronous issues of like thread safety and all that. But it enables you to do more powerful things with less impact on memory. Now, if you really need to go deeper and heavy parallelism things with Dart, you can go with FFI, and then you can code that part directly in Kotlin or Swift, and you'll succeed there. And it's really not a factor for most apps. Like 99% of apps don't really do heavy parallelism work within their code. Now, if we look at more like dev experience or like tooling, dev tooling, we'll start with hot reload and explain with what we learned earlier, we can now understand how hot reload really works. So we saw that Dart has just-in-time compilation, but also ahead-of-time compilation. So in debug, basically it's using Dart as just-in-time compilation. So it lets run the Dart code on the VM, and then you can update the Dart code. So there's kind of hooks with your IDE that it kind of updates the code that's running as you're executing, and that's how you can get like instant feedback. You change a button in your code, and you can see it on your simulator or on your device instantly. So it's the just-in-time mode that enables that. We can, like, if you want to go, when you run Flutter run debug, it will use Dart in JIT mode, which enable hot reload. If you do Flutter build IPA or bundle, it will use Dart in AOT mode, which will not have the hot reload functionality. Now, another like developer tooling that is quite impressive to understand how it works under the hood is code push. So what's code push? You might not all be aware of what it is. So it's the ability to bypass over the air like app stores. So you can push updates to your code and to your users without going through the app stores. It's a great safety net, like if you need to push a hotfix, for example, things like that. And the updates will reach all your users almost instantly. So even if they don't have auto updates on on their phone or things like that. So again, you don't want to do that for every single update you're doing, but it's good to have this baked in your application as a safety net if you have an urgent change that you need to introduce. On TypeScript in React Native, you have the option with Expo via their Expo application services. You can leverage that functionality within your application, either paid or self-hosted. And with Flutter, as of last year, I believe it's via Shorebird that they offered it as it's paid because they have server costs, but I encourage you to look at the pricing and see if it fits for your use case. But really, how does it work? So I'll start by remember Dart as JIT and AOT mode. And functions in a JIT, like this part is a bit complex, but functions in a JIT runtime need to be aware that they have multiple representations. So because JIT compilation, usually because they don't want to have like a huge hit at startup, it will compile very quickly the code, like in a dumb or like not optimized way first, to compile very quickly. And then as it runs your code, it detects which method is being called the most, and then it will say, oh, that one you're calling it like 1,000 times, so it's probably worth to recompile it in a more optimized way. So it will kind of change that method on the spot for a more optimized version. So at the runtime level, like the mechanism to have multiple representations of the same method, so like the regular method and the optimized method is there. So Shorebird is leveraging, it's not using JIT, but it's leveraging that functionality at the runtime level. Shorebird also created an interpreter that's compliant with the App Store policies, and they replace part of your code at runtime without compiling new things. So in your app, basically, what Shorebird is. It's a fork of Flutter to add this like mechanism really low level in the framework. They modify the Dart runtime to add their interpreter to interpret Dart code on the spot. And at up launch, it will basically check the server, the Shorebird server, to see if there's a patch to download. And if there's a patch, it will download it, and on your next launch, it will execute with that patch. Unmodified code will still run as AOT, so you still get all the performance like necessary, and the only impact is the modified code will run as the interpreter, and that modified code will be very, very small. And remember that most of the Dart code in your app is Flutter framework, and that part you're not changing via a patch, so all of that stays as AOT and everything. In the toolchain, Flutter also modified the compiler to create patches and have like that logic to make like between two compiled outputs, what's the smallest difference, and that's where they kind of define a patch and then store it on their server for users to download later on. And in the cloud, they have, of course, offer like the admin console to the management, and they serve patches to mobile users. So because every time the application, there's a patch, the user will get to download that code, so that code comes from Shorebird servers. And now I wanted to dive a little bit into, we've seen like how mobile apps work, but now how do you integrate AI into your mobile app, and how it works, kind of the differences between the different concepts. So if we look at AI, if you use like Gemini Pro or any cloud LLM, basically you have, again, your application code, you want to summarize this text or whatever is your need, then you would build a HTTP call or use the SDK, get to the cloud, come back with your answer, display that to your user. If we compare to Gemini Nano, for example, you would do the same application code, have the same type of request, but then you would use the Google AI Edge SDK, which is like just a pub.dev package, and it would stay on device, reach into AI Core that's installed on all the Android devices that support it, which is Pixel 9, 10, and the Samsung S25 series. So it seems like all the phones releasing this year have it. So we can assume the future phones will keep that support. The list is on the website where you can see all the supported devices. So the request really stays local and comes back to the application. The third way is to use a local custom model, like Gemma, for example, but you can also find very small ones that are very specific to your need. So the difference would be you would embed that local model within your application code. So either it's part of the assets that you get when you install the app, or you download it at runtime during, like, as you need. You'll download it and just like you download an image, basically. And then you would load that model and run the inference within your application. So if we put them side by side, like the first one is the most powerful. Like you get the very large model, but you're going to the cloud and there's some API cost to it. The other two have no API costs. There's a huge concern about privacy, where everything runs locally. So for stuff that really are like really personal to what you're doing, that can be a huge factor. But obviously you have limited intelligence and context if you compare to the other LLMs that are on the cloud. If we look at, for example, most cloud LLMs, you're gonna have like 128,000, or even with Gemini up to over 1 million tokens. Gemini Nano, it's more like between 1 and 4,000 tokens. So it's like magnitudes smaller, but they can still be very powerful for like niche needs. Right now, like it's already used in some Pixel applications, like Talkback. It's the accessibility application. It's already leveraging Gemini Nano to describe images or things like that to users who need that. You're already using for years local AI for like your text, autocorrect, text smart replies and all that. That's generated on device. It's not reaching to Gemini Pro every time you type a word. So those are great examples. And they released also a Pixel Journal application, where it's basically for like your personal journal. You can write your notes, how you're feeling that day, things like that. And so that's not the type of information you really want to send to the cloud every time. So it's running Gemini Nano to kind of bring you suggestions or follow-up questions like, oh, you were feeling stressed yesterday, how are you feeling today, things like that. So they can generate that question and engagement within the app with Gemini Nano while staying really private. So those are kind of ideas of use cases you can do with local AI. So that kind of sums up my talk for today, and I would be curious if you have at least 2 questions for me before we finish.